Dead, dozens injured after a rail crash in Hertfordshire. The train lies in two pieces after derailing at high speed.
This incident was caused by rolling contact fatigue, also known as RCF. It is where stresses in the rail cause small cracks unprecedented in previous slow locomotives. These small cracks slowly propagate into the rail over months. Once they reach a critical level, the rails will just break, causing derailment, as shown in these images. Currently, Sperry UK provides a service to scan for these deformations using specialized equipment like the Roller Search Unit, also known as RSU. These specialized vehicles are used to scan rails to detect for RCF. This is an example of current implementation where RSU is rolled over the tracks. This technique is able to operate at speeds up to 25 miles per hour. The Roller Search Unit consists of an array of eddy current sensors to detect for RCF as it is rolled over the rail. The theory behind this is that the cracks within the rail cause an interruption to the eddy current path, and the change in impedance can be measured using an electromagnetic coil. The aim of this project is to develop a system that can operate more reliably at higher speeds. This will be a departure from existing contact methods, and a contactless system is proposed where an air gap between the sensor and the rail is introduced.
The project has been split into multiple subsections. The approach of each subsection and its outcomes will be shown. Here you can see the final implementation. It consists of several components, including a microcontroller and a robotic arm. Also, you can see the sensor circuitry and its connection to the DSP board.
The simulation work proves the theoretical feasibility of contactless rail inspection with a visual discontinuity of current density where the slots are found. The data was then exported to create plots showing responses of different cracks at different lift-off values from 3 mm to 8 mm.
The sensor circuitry design includes three types of amplifiers and a bridge circuit: the inverting amplifier, the voltage follower, and the instrumentation amplifier. The instrumentation amplifier is used to amplify the output from the bridge circuit. The eddy current sensor is represented by the coil in this project. This is the implementation of the circuit design.
The DSP board was used to process the sensor signal values.
The test platform involves a robotic arm simulating the linear movement of the train, where it will move the sensor over an industry standard calibration block. This allows us to experiment different liftoffs and varying the air gap between the sensor and the rail. We have combined the works of the sensor circuitry, the DSP, and the robotics to make this test platform. The results were acquired using a LabVIEW user interface as shown on the right.
The sensor responses are demodulated into high and Q values, which then can be analyzed using machine learning models. Due to limited sensor responses that can be generated from the calibration block, the existing data provided by Sperry was used to build convolutional neural network. The model showed a performance of more than 90% accuracy on both training and test sets. The model showed lower performance during cross-validation, which implies room for improvement in the generality of the model.
In terms of future work, more complex geometries of cracks can be used to produce better simulation results.
In conclusion, a prototype system was built. It was designed for detecting defects in rail tracks using a contactless sensor.